Well, it is past time to get started, so let's get us started and make a quick comment that I think is the obvious. We are now switching gears, going to our last segment, and I think one of the more interesting subjects or topics, although also at the end of our whole book here and at the end of the sequence, this idea of the modern physics is, like I said, is just like all of ours, and I got to keep telling myself, oh, I wish we had more time, but we don't, just like we didn't have all that much time to do the optics in all its glorious detail, or the thermodynamics in all its glorious detail, or our mechanical ways. But as we get to this last topic of the semester, we'll spend as much time as we possibly could and show you some interesting things, and if nothing else, I'll leave you with hopefully a flavoring, and hopefully even a positive flavoring, of modern physics and modern science, even though, as you'll see, in terms of engineering, it's kind of, for lack of better words, not mainstream engineering, since one of the first things we'll talk about is only relevant as we get close to the speed of light. And other than a few minor cases, or just a few cases, that's where modern technology is. We don't really go close to the speed of light, or we don't need times accurate to a billionth of a second. But there are some important exceptions to that, and GPS systems are a good example of that. But the science part now really begins to come out as we kind of enter this last phase of the book, and you guys begin to go your own separate ways, both academically and literally as you transfer on to other schools. But the idea is that some of you will go into, well, there's computer science, and some of you will go into mechanical engineering, and some of you will go into science in general. And so some of you will see more of this, others of you won't here. But let's talk about what I would call the pure science now as we start to get into modern physics here. And the author begins here in chapter 39 and calls it relativity, and says, okay, what is relativity? What do we mean by that? And maybe I'll put in parentheses here to emphasize that what we mean here is how somebody might look at the speed of something. That's where we'll get started, relative speeds. And again, this isn't really too new. It's going close to the speed of light that is going to be new. Because if I was driving in my car down the freeway, say 70 miles an hour, and a car goes ripping past me at what you might call 80, that's 10 above me, right? In fact, about an hour ago, that actually did happen. I was going down the road, and I won't tell you how fast I was going, but it was more than 70. And they still went ripping past me, and I was like, wow. And, you know, I was trying to gauge it from my perspective, and it looked like about 15 over my speed. And I was pushing 80 as it was, so I thought, oh my goodness, this person is flying down the road. And so my perspective, I'm thinking, okay, they're going 15 miles an hour. But of course, somebody on the side of the road saying this is close to 95 miles an hour as they're going down the road. And so again, these speeds are relative. Now, that's not even close to the speed of light, but it kind of gets the flavoring that relative speeds is really not so much the issue. It is relative speed and a discussion of faster speeds that we want to get into. And that's where we're going to get started here. We could get into relative positions. For example, you might say something to the effect of, well, how far is it to the door? Your perspective of how far is it to the door is different than my perspective of how far it is from the door. And of course that makes sense to you. You go, well, yeah, because you're in a different position. But if I took the position from you to me, and then from you to the door, I would kind of figure out what the distance is from me to the door, right? And so it's relative, positions are relative, but there's a connection between them. All right. We're going to take another look at that. Relative time, I don't know if that such a big discussion in what I will eventually begin to call here our old physics as we begin to get into some new physics. And so maybe I'll just leave that alone here for a moment and say, let's continue on here. Because one of the first words I want to throw out here is to say, for the last either 2 or 3 semesters, or 3 or 4 if we count Physics 102 in there. But for the last 2 or 3 semesters, and maybe I'll just call it 3 since this is the end of the book, although I know some of you haven't done the Physics 122, and half of you, maybe even more than half of you, next fall we will. But this at the end of the book is really what we would call classical physics. It's the physics that kind of began with Galileo and Newton and the mechanical laws, and from then we did our other ones like thermodynamics and electricity and magnetism if you did Physics 102. But all of this really fits into a category of what we call Newtonian physics or classical physics. And when we looked at it, we did things like this. I mean, one of the things that we did back here in classical physics is we said the kinetic energy is 1/2 mv squared. I mean, that obviously takes us back to Physics 121. We did that in Chapter 7. Oh, we also got that, if you recall, by saying this is the integral of the work. And the force, at least net force, was mass times acceleration. I mean, clearly Newton there. This is Newton's second law. And so this all is referred to then as classical physics or Newtonian physics. And that's what this last unit is about, kind of introducing you to something beyond Newton and really showing where Newton's laws are incomplete. They were not perfect. It's probably a terrible thing to say after 3 semesters of some really hard work, but we did it all wrong. Well, that's a little strong. We didn't do it wrong. We did it approximately right. There's more to it. And that's what this next section is. This next section is saying, let's look at some new extensions of Newtonian physics. Probably the best experiment, it starts with an early example. And so let me go back in history. I think kind of to make this make sense, you have to realize what was happening at the end of the 1800s and the experiments that were being done. One of the common one was to take a little electron and a metal plate, charge it positive, and let this positive charge pull the electron, put a little hole in it, and look at the kinetic energy, or to look at the speed of that electron. How fast is it going? Now, for some of you, this is kind of an unfair discussion because you haven't done electricity and magnetism. Others of you have. So I won't dwell too much on it, but I will remind you of this idea back in Physics 121 that if we do work on an object, whether it be a big object like a car or a little one like an electron, its kinetic energy should be equal to 1/2 mv squared. And that's what this little electric field would do, whether or not you've had time or had the class yet to talk about electric fields. So one of the early experiments would charge this plate up to 200,000 volts. And so you can kind of see in history that we needed to really understand electricity first, and then from there, little electrons, before we can get things going really, really fast. And so let's say we charge it up, and maybe I should spell it out for some of you who haven't gone through there, but we've got this at 200,000 volts. The work done on it is the charge of the electron times the voltage. Now, again, for some of you, you don't know that, so I'm just going to say that. And again, it's not the electricity part I'm really interested in. It is the moving electron that I'm interested in, because if I put the charge of the electron, and then I put in my 200,000 volts, and I set that equal to 1/2 times the mass of the electron times speed squared, what do I get? And so, again, into the late 1800s, these experiments were performed. And they get a speed that comes out to be about 88% the speed of light. Now, let me pause right there, because this is probably worth mentioning. What is the speed of light? All right, we just got done with our optics, obviously, so it's 3 times 10 to the 8th meters per second. And of course, we could actually mathematically multiply this out, but we usually don't. We usually start to write things as a percentage of the speed of light. So instead of me just putting a big number over here, let me just say this is a fast speed. This is 88% of the speed of light. And when they first did this experiment, they kind of hooked it up. They measured the speed. They noticed the speed wasn't quite 88% of the speed of light, but you know, they probably blamed it on their partner and said, well, within reason, we got that. But here's the most interesting part of this, is then they said, well, as our technology develops, maybe we should charge up the plate even more. How about 400,000 volts? And so whatever it took to eventually get to 400,000 volts, we can then run the experiment. Now the reason that's a nice number is because isn't that twice as much work here? And so we would have a different number here. We would have still the charge, 1.602 times 10 to the minus 19. We would also have then this 400,000 volts. We would set it equal to 1/2. We would set it up to be 9.11 times 10 to the minus 31. We'd get v squared. And if you actually get your calculator out and do this one, you come up with about 125% the speed of light. So the idea is, okay, we'll make it go faster than the speed of light. Great. Well, some of you laugh because when you actually try this experiment and then measure the speed of this electron, it is not greater than the speed of light. It is only 96% the speed of light. So it doesn't do this. Not. Why doesn't it do that? Could my partner really make that big of a mistake? I don't think so. So what's going on? Well, maybe the best thing to do here is to quote Einstein and say what he and many others begin to notice is something's just not working right. It's not the experiments. We've done too many of these, although, of course, I'm just talking about one. But after they have done many experiments and many discussions, they begin to realize that something is really wrong with Newtonian mechanics. Something is really wrong here with the way we understand physics. It is just not working out. It's not that we are doing any of our measurements wrong. In fact, the more and more measurements that are made, the more and more the evidence begins to come in that it doesn't matter what you do, it doesn't seem to ever go faster than the speed of light. And of course, at this point, why? Who knows? But it is becoming very, very clear that something more than just Newton's laws of motion. There is something more than F equals ma, because F equals ma leads directly to 1/2 mv squared, which leads directly to the fact that these electrons should and have the potential to go faster than the speed of light, and yet they don't. And no matter what they've done, and they did a bunch of other experiments too. I'll just show you two. This is the first one, and it's just not working out quite right. In fact, a chart, it can be kind of helpful at this point because I'm trying to emphasize to you that what we've been doing, which we kind of call classical physics, we are going to overwrite. We are going to redo. Starting a little more than 100 years ago, science began to realize there is something else here. Mechanics is a bit more complicated than what we've been led to believe for 200 or so many years. And so I kind of like this chart. This kind of helps me keep my thoughts process. It's a graph, if you will. It's more of a picture than it is a graph. I'll put speed on one axis and I'll put size on the other axis. Because really, if you think about everything we really did, is we did things, I'll put a dotted line here, representing things that are about the size of an atom. Maybe I'll put 10 to the minus 10th there. And everything we've been talking about up to these 3 semesters really has been bigger than the atom. We've talked about things like cars moving and airplanes moving, spaceships moving, but they've all been kind of big objects. I'll put another dotted line here. I'll put a solid line here. The solid line I'll represent with the speed of light. I'll put another little dotted line at about 10% the speed of light. Because what I'm trying to point out here is we've done everything with what you might call a slow speed. Now, you might look at the spaceship or a rocket ship and look at its speed of 17,000 miles an hour or 25,000 miles an hour and go, well, that's not a slow speed. But it is really slow compared to the speed of light. And so when I say slow, I mean slow compared to the speed of light. And so this little area, this box here, is what we've really been looking at. Newtonian mechanics. And the question is it completely right? Would it still work at fast speeds? Would it still work with small objects? And if it does, great, then we understand our physics completely. If it doesn't work, what does that tell us? Well, it tells us that there's more to the world going on than what we first discovered. And our understanding of science needs to then evolve. We need to see what more complicated things are going on out there. And since we ourselves don't tend to go very fast, or we ourselves don't tend to be very small, these things that do go very fast or very small could have properties that look bizarre to us. And that's hopefully what we'll come across here before today's over. We'll see some things that you might find a little odd to believe if you haven't been exposed to this before.
Is nothing allowed to go fast in the speed of light?
So I put a solid line there because at this point I just said nothing we've measured goes faster than the speed of light. We'll go through Einstein's technique of redoing the old theory, and you'll see also in his it predicts nothing goes faster than the speed of light. So as we currently understand it, I will say nothing goes faster than the speed of light. Now, that doesn't stop us from always questioning, well, what if it is? What would be the consequence? And then once we know the consequence, should we start looking for it? We even give a fancy name to anything going faster than the speed of light, and these tachyons. But it's just discussion. So, no. We have no measurements, no matter how hard we try. We have no reason or no theory to believe we ever could get faster than the speed of light. And you'll see why, hopefully, here in just a second. But what I'm trying to show you here is this. What I would call then Einstein's mechanics. You might want to call it relativity. And that's where we want to start with this chapter. We want to look at what would happen if you go close to the speed of light. What new things come into play? And this is a first good example of an experiment where clearly something more is going on. This is not the whole story. If this was the whole story, then we should get this speed, and we don't get that speed. And so why don't we get that speed? What else is going on? The next chapter, we will begin to see that F equals ma does not work there either. And so for many reasons, we will see that F equals ma was a wonderful start. And I think that's just our way of saying we don't ever want to say Newton was wrong. We just want to say he's incomplete. And so we'll continue on with our knowledge and our learning lessons that goes on here, and we will discover here that, hey, there is more stuff going on. Those of you who had me for 122, you saw this on the last lecture. Left you with maybe a weird taste in your mouth, because we spent the whole semester talking about magnetic fields, only at the very end to say what? The magnetic fields don't really exist. They were a human perspective of a misunderstanding of what really goes on at close to the speed of light. And so we have to kind of modify our thoughts. Now, don't get me wrong. That doesn't mean any of the stuff that we did in Physics 122 is useless by any means. What it means is we can still do and think about magnetic fields. They work great in terms of building a magnet and putting it on the wall, and building a magnet and making a motor, and building a magnet and making the locks on my car go up and down. But they really aren't the science of what's going on, and that's this whole idea. And so there becomes a kind of a divide now between the science, perhaps, and the application of the science, and how do we want to apply it. So I'll say the same thing here. Although we're going to go into here, don't forget F equals ma. Don't forget the kinetic energy is 1/2 mv squared. If you find yourself in a career where you're building a car, go ahead and use F equals ma. Unless this car is going 90% the speed of light or something. It's fine. Continue on with the same process. That's not really the point of this introduction. The point of this introduction is to say there is more going on, and we don't have to consider the more going on unless we are getting close to the speed of light. And like I said, that's our first step. So that's the introduction to the introduction of modern physics, is to say that there is quite a bit more going on, and I think that picture shows it really well. All right, here's another good experiment that shows it really well. It comes right out of our optics and our interferometer. And so the lab we did this week, or for some of you will do today, is to kind of take a look at the interferometer again. And it was Michelson, and I guess his buddy Moret, and so the Michelson-Moret experiment, who said, let's try this. The Michelson interferometer, if you recall here, was taking some light. In the lab, I'll call it laser light. They didn't have laser light at their time, so we'll call it sunlight or something, but some light. And if you remember, it hits that little splitting mirror, bounces off, and comes over here and hits one mirror, and hits over here another mirror, bounces off, comes here, bounces off, comes back, and we look up here on a screen and ask ourselves, well, what are we going to see? And maybe for completeness, I'll point out that some light goes over there. And so the 3/4 of you that have already done this lab, you noticed that what we had in the center was a dark fringe or a bright fringe, or maybe even something in between. It all depends upon the spacing between these two mirrors, the relative spacing. And in the lab we moved the mirror a distance d. Well, it was Moret who came to Michelson and said, hey, let's use your interferometer because I've got an idea here. I've got an idea to kind of figure out how fast is the Earth moving through the universe. And his idea makes sense, at least for the science known at the time and the science you have been taught so far. He said, look, here's, say, the Earth, and the Earth is moving around the sun. We know that much. What we're not sure about, though, is how much is the solar system moving around the Milky Way. And I'm not even sure if they knew that much. But even then, how much then is the Milky Way expanding out? And I'm sure they didn't know the Big Bang in that point. And so that was just the question. What is the overall speed? And here's their logic. Their logic is, if I were to perform this experiment with this interferometer on a moving object, how would I analyze it? How would it be different than if it was on a stationary object? You see, what we talked about in our optics is as if the Earth was stationary, as if the Earth wasn't moving. And if the Earth isn't moving, what would happen is it would go down and back, it would go down and back. Let's just say that those paths differ by some number such that you get a dark spot right there. Okay. We know then, if you move the mirror, it changes from a dark to a bright. But what if it was moving? How would this little discussion, how would this interferometer be discussed and analyzed if it was moving? And let's just say it was moving in that direction. And so this is why, as I said, Moray came to Michelson and said, you know what, let's re-look at your interferometer, but let's do it from a viewpoint that the Earth is moving for a second. Because if you do that, what happens is it would look as if this mirror was moving along. And so the laser beam would come in, and let's say, here's the light as it leaves. Now, at that point, here's the mirror. I'll call that T naught. But as time goes on, the mirror is going to be moving back. Now, how far it moves back really kind of depends on how fast the Earth is moving, or wherever this object is that is doing it. So it's moving back a little bit, but of course the laser light is going at the speed of light, so it's going to catch it, right? And so maybe that beam hits right here. I'll call this T1. Then the light reflects back, and this mirror may be back here to T2 by the time the light comes together and hits this splitting mirror, because the splitting mirror is kind of doing the same thing. T naught, T1, T, actually maybe I should call T naught when it actually hits the splitting mirror, T2. So by the time it gets back, it actually hits the mirror right there. Fair enough? And then that's what goes off to the screen. And then I think you'll see that the distance that this beam traveled is not simply that doubled. The distance the light traveled would be a bit more complicated. Now, let's not go through a complete analogy how to discuss this, but I think you can see that I would have to take the time it would take to go from here to here to hit the mirror, then from here to here to get back to there. Fair enough? And I would call that the distance of that light path. And then let's look at this one. How about this guy down here? Well, again, when the light beam hit the splitting mirror, this lower mirror could be thought of as being in this position. There's T naught. But as it comes down, it actually is going to hit right here. Let me call it T1 prime, only to say this is the time when it hits this mirror. But it's probably different than this one, because this one's coming down at an angle and this one's going straight back. And so however much time it takes to go from here to here probably isn't the same as it takes to go there to there. And then likewise, here will be T2 prime, where it comes back and meets up with right there. And that's a little big picture. Maybe I should have just I went past my mirror. But it would be 1, 2, 3 or something like that. And as I said, this would be a fun derivation into analyzing it. You actually did this. Do you guys remember the swimmer problem at the beginning of the semester? No? You had a swimmer on a river. You had two swimmers. One went across the river and back, and the other one went with the river and back. And the reason I picked that one, even though it was way early in the semester and very few seem to remember by the time we get here, but by the time you go through all that derivation, you were supposed to come up with that these times weren't equal. And so the effect you see on the screen is different than what you would have seen here. And really that's all we need for today's discussion, is to convince you that it will be different. Oh, did I see a question?
Oh, is the laser standing still, or is it?
Well, then the laser would be moving too. So the laser on the table in the classroom, they're all moving along on the Earth. So, but here was then the Michelson-Morley experiment. They said, we got this. Since this pattern would be different this way and this way, there should be an interference pattern on here because of the different effects with the motion and perpendicular to the motion. That's what I want to emphasize. Because although when you get a pattern on the screen and you get bright, dark, that by itself doesn't tell you anything. But here was their genius. Let's do this. Let's look at the pattern on the screen while we rotate it. And so you mount this whole interferometer, and I think theirs was like 26 feet long or some large amount. And they look at that pattern and they realize, if you rotate this, one arm, which was going with the motion, is now going to be perpendicular to the motion. The other arm, which was perpendicular, is now with the motion. And there will be a difference between those two, and the change will be shown up on the screen. And the fringe pattern they could count. Bright, dark, just like you guys did in lab. And from that information, we should be able to figure out how far the mirror moved, which is really telling us how fast the Earth is moving. Ah, brilliant, right? So they give it a try. Guess what they find? Nothing. Absolutely nothing. Frustrated by it all is why they kept building bigger and better interferometers, going, there's got to be an interference pattern. Now, I suppose you may argue, well, the Earth's not moving then. Well, they decided to wait a half a year because perhaps they just were at the right spot when they did the experiment and the Earth wasn't moving. But they know 6 months later they're going to be moving the other direction. So they try it again 6 months later. Guess what they get again? Nothing. Right. So, this is often referred to as the most famous null result. Because it looks like something is not going as planned. But what they indirectly discovered is the same thing on that first experiment. What I was trying to show is there's something about the speed of light. Something that is more than just the speed of light. In fact, I wish we would change the name speed of light to universal speed or speed of the universe. Yeah, because speed of light does not give the true justice behind the physics of this number. There is an important idea behind this. There is something about built into the universe about that speed. And we as humans discovered light going at that speed for the first time. But that's long before we discovered the speed, say, which gravity goes. Because it too goes the speed of light. And everything we discover goes either less than the speed of light or at the speed of light. And so this speed of light is, as I said, far more important. And so this null result actually opened the door to Einstein here. Although I guess there's some historical debate whether Einstein even knew about this experiment or not. But let me go with it. He certainly knew other things about it. But one thing that didn't seem to make a whole lot of sense, yet seem to be true from the experiments, is that all observers seem to show that the speed of light is 3 times 10 to the 8th meters per second. It didn't matter how fast you are moving. You see, here was the argument. The argument was, very simply, that the reason you plan to get a different pattern on here is because when you go to analyze this, like you guys did for the swimmer in the river, is you analyze it by saying, if the mirror is moving backwards, say here at half the speed of light, and then the light is traveling towards it at the speed of light, you say it is then approaching, if you were on the mirror, let's say, looking at the light, and you're saying, okay, come here, light, bounce off the mirror. You're looking at that light, and you're saying, well, it's traveling half the speed of light. Well, if the light was still coming at the speed of light, even though I'm moving at half the speed of light, then we would still analyze it the same way, and then if we rotated it, it wouldn't matter how much the Earth was moving. It could be moving a little, it could be moving a lot, it was all irrelevant, everybody would see the speed of light the same, and so this kind of brings up that question. Is it possible that the speed of light looks the same, regardless of how I'm moving? So if I'm on this mirror moving backwards, I see the light still coming to me at the speed of light? Is it possible then that if I'm on the mirror sideways and the light's coming down at an angle, is it moving the speed of light? Could it be possible that if I'm in a spaceship going this way and I turn on my flashlight and the light goes out and my spaceship is going half the speed of light, the light leaves at what speed? The speed of light? Or does it leave at half the speed of light? And if it leaves me at half the speed of light, what does it look like to you? And so the whole point of this beginning part is that our experiments begin to show something interesting about this speed. It wasn't just the speed of light. There's something more here in the fundamental nature of the universe. And as bizarre as it may seem, here is kind of Einstein's approach. He says, look, let's just take this as a given. We call this the first postulate then of special relativity, and say, look, without explanation, that's why it's a postulate. Let's start here. Let's start with this idea, because that's what the experiments seem to say. I don't really understand why. I'm not even going to try to understand quite yet, but I'm just going to start by saying, if I'm in my spaceship and I go along and I shine it, how fast does the light go away from me? Well, since it's light, it goes the speed of light. And so the fact that I am going half the speed of light and I shine it, it still goes half the speed of light. And if you, sitting on the side, watch the light go away from my spaceship, how fast does it go? The speed of light. And so that's where we want to start. We want to start, is that even possible? It doesn't seem like it, does it? But here's where the brilliance of Einstein comes in. And I should probably even say the boldness of Einstein comes in. Because keeping in mind these experiments, keeping in mind that there seems to be something universal here, something about the speed of light, let's do this. Let's kind of run a simple experiment here. Let's do this. You'll notice that a lot of these discussions involve trains, because that's how Einstein explained it all, which I think in our time and age, or maybe not our time and age, but at least our location in the world here, trains aren't that very common to us. We should change it to a car, I think, or something. But nonetheless, the Einstein had his apartment, was it his apartment or his office? Well, one of the two, overlooked the train rail station and the switching cars. So he kind of analyzed, he goes, I wonder what would it look like from that point of view, and what would it look like from this point of view? And so as these trains would come in and out, he began to think along those lines and say, okay, what's going on in this train? So let's do this. Let's put somebody in the train for a moment, and let's take two views. One of you being in the train, one being out of the train. For discussion, I'll say I'm in the train, you're out of the train. All right? Now, if I'm in the train, and for simplicity, let's say I take a ball and I throw the ball straight up. Just to make some round numbers, let's just say I throw it up at 30.
In a train.
Huh?
Too fast.
Well, that's why I was basing on the units. I was going to say 30 meters per second, but, well, that'd be about 66. I don't know. Yeah, I might still be able to throw a ball at 66. I don't know. But, okay, would you feel better if it's miles per hour? I could do that. 30 miles an hour. All right? I just been wanting to stay away from the English system, but all right. But nonetheless, I'll do the 30. And then the train, let's say the train is chugging along here at 40 miles an hour. And I just wanted to pick some nice even numbers so we could do this kind of quickly in our head. I would see the ball go straight up at 30. Fair enough? What would you see? Yeah, you would probably see this parabola in its shape. But let's just talk about its speed right here. What would you say its speed is? 50. How'd you get 50? Right, we went back to physics 121, right? You said, well, this is Pythagorean theorem, right? If I have a horizontal leg that is 40 and I have a vertical leg that's 30, I would add the two together. And I'd get 50. And so basically what you did is this. You said, I'll take the horizontal speed, I will combine it with the vertical speed, and I'll get the total speed. Fair enough? But why did you do Pythagorean's theorem? Because I told you how to do that in physics 121? Yeah. Well, good thing Einstein went a step further. Why did I tell you that it would work that way? What was the reasoning behind? And this is Einstein's brilliance. He says, well, wait a minute, let's see. I guess it would be something like this. What if we take a look from the inside? The inside might look something like that. We may say that it goes up a height h, as it maybe goes up to the top. And let me just do this without gravity, just to kind of keep it simple. Obviously, there would be gravity slowing it down here. But just to kind of get to the basic idea here is we would go up and say, okay, we're going to go a height h. And you probably would say then, okay, this is the vertical speed, this is the time, this equals h. Fair enough? If it was outside, or if somebody was watching from the outside, so you guys are watching from the outside, you would have taken this ball and you would have said, well, it's really doing something like that, right? It's off at an angle. And you may say that angle then is theta. But since it's going to go up and hit the roof, then what I would want then is to know what is the vertical speed. So you might take the speed, multiply it by sine of theta, multiply by time, and get h, right? In fact, maybe I should just, for clarity, not call this the y, but say this is the speed I would observe on the inside, so I'll put inside. This is the speed you would observe on the outside. Okay. If I, just for the sake of discussion, replace sine theta with the square root of 1 minus cosine squared theta, t equals h. And I know at this point you're going, why will you do that? It's like you're making it harder. Okay, but the reason for that is, what would cosine of theta represent here? Yeah, the x direction. So this would be the velocity then of this train divided by v. Fair enough? And I'll say V on the outside. So what I would have, and maybe I'll square everything first so that I can get rid of this crazy square root. So I'll have velocity on the outside squared. I'll have 1 minus, and in place of cosine, I've got velocity then of the train divided by the velocity on the outside. Those are squared, multiplied by time squared is equal to h squared. Fair enough? All right, well, let's keep going. Because even though we didn't do this directly in Physics 121, we really did do it indirectly. We then said, well, here's h, and here's an h. Let me square that. So this would be velocity on the inside squared, time squared is equal to h squared. So when I do this substitution, I get velocity on the outside squared, and I'll just do the distributive property. Here would be minus the velocity squared of the train. Each of those multiplied by time squared would equal to velocity on the inside squared times the time squared. Are you beginning to see how we got it now? Right? I mean, isn't that going to come out to Pythagorean's theorem? I mean, isn't there a time on both sides? And so that time would cancel with that time, right? That is the magical step. I mean, I'll keep going, but when I cancel those off, I get the velocity on the outside squared is nothing more than the velocity on the inside plus the velocity of the train, and there's Pythagorean theorem. So why did it work? Oh, there, it's obvious, right? Pythagorean theorem's pretty easy. I can go through my mechanics, I can work it out. But what assumption did I just make? What? Time's not zero, okay, but I agree time's not zero. It takes a while for it to go up. I have assumed in here that the times as observed by you and me are the same. I wonder why that would be true. Seems true. Well, yeah, right, it seems true. Well, that's good enough. And there's the problem. There's Einstein's genius. His genius falls in right here where he realizes that the whole reason this works is because the times by the inside and outside observers are the same. Let me make a small modification. Here's Einstein's thinking here. And again, maybe I'll do it in red here, because this time right here was the time measured and calculated by the outside observer. This time was for the inside observer. Einstein realizes, and what I'm trying to show you is if those times are the same, then these speeds observed by the inside and the outside person have to be different. And so I see the ball going up at 30, you see it going at an angle of 50. And for all those centuries before Einstein, everybody was happy with this statement. But Einstein realizes that it is this assumption that the times being the same result in the addition of velocities using Pythagorean's theorem, which would give you different speeds. He goes back to the experiments and says, what if this, instead of being a baseball, is a beam of light? And so as it goes upward, the velocity as seen by the inside person is c. If the times are the same, and here's my main point, if the times are the same, there's no way the speed on the inside and the outside observer can be the same. Fair enough? And that's what science had been doing up until this point. What Einstein realized is something new is going on. Something different. Something we did not notice in the past. And what seems to be is that the speed of light is the same. So he takes this bold step and says, I am just going to assume, without explanation yet, just assume that the speed on the outside is also the speed of light. And so somebody in that train who shines a flashlight up, they see it go up with the speed of light. Somebody else who's on the outside of the train also sees it go up the speed of light. Einstein's question is that possible? And what I want you to see is it could be possible if the times are different. And so, are the times by a different observer actually different? Is the time observed by your clock different than the time observed by my clock? Now, let's just assume that's true for a second. What would that mean? Well, here is the main step. If V on the outside is equal to C, and V on the inside is equal to C, then time by the outside observer cannot equal time by the inside observer. There's our choice. We either can assume the times are the same, and then the speeds can't be the same, or we can assume that the speeds are the same, and therefore the times are different. And so let's take that bold step and replace the velocity on the outside with c squared, the velocity of the train with just v, since the other speeds all have a c in them. Then what Einstein notices is right there. Different times for different observers. Let's see if we can work out how they're connected together. I think if you put the c squared over here, you'll see 1 minus v squared over c squared then would equal to the time on the outside squared equaling to time on the inside squared. If I take the square root, I get the square root of 1 minus v squared over c squared equals time on the outside divided by time on the inside. Oh, no square. I'll take one more step, which is the common way of writing it, although so far it might look a little bizarre to write it in the denominator because I did not have a fraction, and now I do have a fraction. But it is standard practice, then, to refer to this ratio of v compared to the speed of light as beta. It is also common practice to refer to this 1 over the square root of 1 minus beta squared as gamma. And so this would become time on the outside is equal to gamma times time on the inside. Now again, let's pause here because this is going to lead to all kinds of crazy consequences, which is what this chapter is about. Because we are now saying here that instead of assuming the times are the same, we are going to assume the speed of light is the same, which means the times are different. Now, I'm sure most of you, or most of you who haven't seen this before, are probably going, wait a minute, I've had a watch. And I've used my watch, and it doesn't really matter if I was in my car or not. Don't tell me there's something different about time if I am moving. But wait a minute, let's look carefully here at the numbers. how fast was your car moving compared to the speed of light? Really, really slow. I mean, just for the sake of discussion, let's just say my car was moving 70 miles an hour. I take 70 miles an hour, I'll divide it by roughly 2.2, and that's about 32 meters a second. I'll take 32 meters per second and divide it by the speed of light. That's pretty small of itself, but this is asking me to do the square of that, okay? So I'll square that. And we're looking at 1.1 times 10 to the minus 14. So if I take 1 minus that small number and square root that, what do I get? I bet even on my calculator, if I go 1 minus that answer, I get 1. And so that's more decimal places than the 10 on my calculator can handle. And so what do I record in my car versus out of my car? A time that technically is different, but I would never notice it at 70 miles an hour. I would never notice it at 25,000 miles an hour. I wouldn't even begin to notice it till probably close to the speed of light. If you remember that little chart that was here, I put a dotted line at about 10% the speed of light. So here's kind of our statement. Our statement is, nature could be working this way. We just never noticed it. We just never went fast enough. Now we're going, with these little experiments, fast enough. And maybe that's why Newtonian mechanics isn't working. We based all of our Newtonian mechanics on the assumption that the times by the observers were the same, and so the speeds were different. But perhaps that's not how the world works. Perhaps the world has the speed of light the same. There's something special about that, and time is different. Now, since we never noticed time was different, then there must not be too much change to time unless you get really, really fast. So in case you think this is too weird and too bizarre, yes, accurate experiments have been done. Yes, they have recorded time differences. Probably one of the most famous ones is just put an atomic clock on a passenger plane, fly it around the world. You put one clock on the tarmac, you put another on the plane, you fly around the world, you land again, and they differ by a few billionths of a second. Okay? Not much, but exactly in the amount that is accurately predicted and accurately calculated. And that's not the only experiments. Many other very famous experiments have been done because, again, this is a bold statement. You need some kind of experimental evidence if you're going to get people to buy in to say that the times aren't the same, because we live in a world where we go slow compared to the speed of light. We're not used to our clocks having different time frames, but they do. In fact, let's keep going. You'll notice I did not box this purposely because I want to make it look like your author has it. Your author, instead of calling it time on the outside, he calls it a delta t, meaning this is some kind of change in time, some kind of a lapse of time. Let me just make sure I use the same notation. Yeah. And then he puts the gamma here, and he calls this a delta t sub p. And this sub p is what we're going to refer to as proper time. Because here is the dilemma we're going to have to work through this whole rest of this chapter. If the times are different for each observer, how do I define time? If you said it took 1 second, does that mean it took 1 second for me? Your time and my time aren't the same. And they're not the same as that person's time over there. So we all get different times. Now on the surface that may sound like, oh, there's nothing we can do with time now. It's completely random. But that's not true either. There is a connection between all these times, and it's the relative speed between them. And so we still have a usefulness with time. It's just we need to remember there's no such thing as one time. It all seems to vary. And it's not just a perception. I know that, sometimes time can seem longer because you got to sit and listen to a 2-hour lecture and it seems like 3 hours, or it seems like a half hour. Or the way Einstein put it when somebody asked him, how are we supposed to understand this relative time? And he said, when you sit next to a pretty girl, time goes faster. And so he was unfortunately trying to give a emotional response or a perspective response, but that's not really what's going on. Everything goes a little bit slower here. Let's look closely at this. This proper time then becomes our reference point. Everybody will agree with the same proper time. And so what do we mean here by proper time then? Well, I did it calling it the inside piece. Let me get away from it, but what was special about that inside piece? Well, the inside piece, there was, I'll say, no motion to me. Now let me see if I can make that a little clear. What my time was, as you guys watch and as I watch, here's the time, right? On the x-axis, I'll start with my flashlight right here. So if I was measuring the position of the light when it got started, I would say the light is maybe 20 centimeters away from me on the x-axis. The light beam goes up and hits the ceiling. Okay, on the x-axis, where is it? Same spot. And that's what I mean by no motion. So the person on the inside, the position of the event did not change. There was no motion for that one. But what about you? Right. And so you guys are in this room. Let's say you pick the origin to be the door. So when I start the flashlight, you say the light starts 3 meters away. But when it hits the ceiling, it's more than 3 meters from the door. It's now 4, 5, or 6 meters, depending on how fast I was moving. Fair enough? So you are the non-proper time. You have moved. Somebody else could be even driving a car. They would be moving even faster than you, or slower, depending on which way the car was going compared to me. But that person too would record a non-proper time. Now that non-proper time would be different than your proper time. Fair enough? Because the speed at which that car is moving relative to me is different than the speed you are moving relative to me. And so we have an infinite number of different times for this event to take place. We have only one proper time. And that's going to be our key to keeping our physics going. It's not just any random, useless time. This is an important one. And so if somebody's in the car or you are in this room, all of you can measure your time, do a calculation, and get my time, the proper time. And so we have now a reference place. And so this is going to be an important discussion. Time. The hardest part of these homework problems really are looking at the problem and deciding, is it proper time or non-proper time? Because calculating gamma is not real hard. I mean, let's face it. What are you going to do to get gamma? You're going to take the speed. You're going to divide it by the speed of light. You're going to subtract it from 1. You're going to take the square root. You're going to take the reciprocal, and you got gamma. The biggest question then would be, now that I have gamma and I have time for the event, how am I going to put it in here? Do I have the proper time or do I have the non-proper time? So there's lots of non-proper times and only one proper time. Let's even make a graph of gamma. If I plotted gamma versus the speed, and again, I'll put a solid line at the speed of light. I'll put a dotted line at 1, because if your speed was 0, what would you get for gamma? Wouldn't I get 1? And in fact, as your speed begins to increase, not much would happen right away, because when you take your speed and divide it by a big number, it's small. You square it, it's even smaller. And so really, you're not going to see much of an effect with the gamma for a long time. Which is why proper time and non-proper time would be roughly the same number for any low speeds. That was the assumption that Newton and Galileo and everybody had done up to Einstein. But Einstein finally now has something to say, you know what? I don't think that works. I know this, that if they're the same times, you can't get the same speeds, and our experiments aren't showing that. Our experiments are showing the same speed. So there's something more interesting in the universe about speeds than there is time. And so he gives it speeds the same and comes up with times being different. And so this gamma function stays pretty much at a 1 and doesn't really start to increase, although eventually goes to infinity as we get closer to the speed of light. And so this imbalance of time, proper time versus non-proper time, does not really begin to show itself until we get to about 1/10 of the speed of light. And this isn't really drawn to scale. I guess 1/10 of a speed of light would be back here on my scale. But to emphasize that most of the things that we do in this world are here, less than 10% the speed of light, then we won't worry about gamma, and that's how we've learned our physics so far. We have learned our physics essentially by saying gamma is equal to 1. And now this introduction to modern physics is beginning to realize that, oh no, the world isn't that simple. Wish it was. I bet you never even thought it was that simple when you were doing this semester, or last semester. But it is more complicated than that too. More stuff is going on. Now, let's think of it this way. Let's say I was holding a clock in my hand, this watch, and I'm in my spaceship. I'm moving along. I'm looking at my clock. You have maybe a telescope and you're looking at my clock. All right. As I'm looking at my clock and you're looking at my clock, who's measuring the proper time? Is it me?
Yeah.
There's no motion between me and my clock. Right? Here's my clock. It's 10 centimeters away. Time is ticking. Maybe I'll let a whole hour go by. I look. It's still 10 centimeters away. There's no motion of that clock to me. So there's the proper time. So you would be measuring non-proper time. I would be measuring proper time. Let's say I record an hour. What would you record? Would you record an hour too? More than an hour? Less than an hour? Well, would gamma be more or less than 1? So if I measure an hour, 1 hour, and let's just say I'm going at a certain speed, so gamma comes out to be 2, you would measure 2 hours. And so the non-proper time is going to see the time tick away. Maybe you've heard the story of the twin paradox. You take two twins, and immediately at birth, you put one on the spaceship, and you leave one at Earth. This one on the spaceship keeps going along. As far as this little baby is concerned, the people on board take care of the baby, and then they have the 1-year birthday party. Yay! People back on Earth want to see this birthday party. So they get their telescopes out. And they look over here at this spaceship that's, of course, really far away by now. When do they look at this 1-year birthday? Would it be same as 1 year for them? No. Would it be more or less time? More. Depending on how fast the spaceship, it might be 10 years. So the twin is back here celebrating 10th birthday party. They're signing up for Little League, right? Hey, let's go play Little League. This baby over here is just learning to walk. The time is different. And so we got to think about time a lot different than we have been. Time is like this flowing of water in a river. And you take these two babies on a raft, and the river separates. And if one river goes faster than the other, this baby only goes 1 year or 1 mile. But this baby goes 10 miles. They're not the same distance down the river, are they? They didn't flow at the same rate. Time didn't flow at the same rate. Time, then, is different. And it's not just because the batteries in the clock were running slow, right? I mean, if the batteries on the clock just ran slow, you would turn the pages on this spaceship of the calendar, you would get to its first birthday party and say, you know, you're a pretty big kid for a 1-year-old. You can walk and you can talk and you're ready to play baseball. God, what a precocious little kid you are. 1 year old. No, everything. The speed of the electrons, the pumping of the heart, the consumption of fuel on the spaceship. This is a fundamental part of nature. The flow of time is totally, totally different. And this is what I call the first bizarre consequence of our modern physics. That time is relative.
I'm confused. So the kid on the spaceship will actually just be turning one and
just turning one.
The size of a regular 1-year-old?
Oh yeah. Yes, again, these are not just weak batteries. The spaceship comes back to Earth and lands and said, oh, I get to meet my twin brother. And so out comes the twin brother who's now 20 to meet his toddler twin who is 2. Time is a lot different than you have been exposed to so far in our science and in our physics. Time is relative. Now, I will point out, notice then that time went forward. Some people get the wrong impression of this, like, oh yeah, so I'll take my spaceship, I'll go out, I'll come back before I was born. I don't know, shoot my mother and I never get born. Some weird science fiction stories, all kinds of weird things. None of that was possible, right? Time went forward. Time did not go back. This was not time travel going backwards, changing the past to affect the future. That was probably a bad example. Maybe I should shoot my arch enemy's mother. There we go. Then that'll never be more. Make you feel better. Okay. All right. But time went forward for everybody involved, regardless of what it is. Here's a nice phrase to keep in mind. Moving clocks run slow. That's the way I like to think of it. It helps me keep it together, proper time in my mind that, hey, if I have a clock that's moving, it's running slow. And again, it's not running slow because the batteries are weak. Time is not a human invention. Time is part of nature. How long does it take for the Earth to go around the sun? That is time. How long does it take for the electron to orbit around an atom? That is time. When we build an instrument out of it, like a watch, to measure time, yeah, that's a human design and a human invention. But time is there. Time is something that takes place outside of human perspective. If there's no humans, there's still time. Just like if there's no humans, there's still distance. There's a distance between the sun and the Earth. There's a time it takes for the Earth to go around the sun. Humans or not.
Which one was the proper time in this spaceship example?
Good. It does get difficult because so many different, everybody has their own time now. And so the short answer is, look at where the clock is. Okay? That clock is going to be measuring, if there's no motion between the observer, and that clock, that's proper time.
So because you said that they were celebrating up there, so they were the proper time, and so then here's longer because we're dividing by gamma.
So proper time would be, say, 1 year.
Yeah.
And then gamma, I'm going so fast that gamma is equal to 10.
Why would gamma be 10? Oh, because the reciprocal of 1 over a small number.
Right.
Okay.
Right. So gamma is always greater than 1 and could be big like 10. whatever speed is needed to make it a 10. And so the non-proper time is 10 years. Here's the paradox, though. Well, we've never had twins separated at birth going close to the speed of light. But another good experiment, I'll mention it nonetheless. A real good one is Earth and cosmic rays. When the cosmic rays come in and hit the upper atmosphere, they create radioactive particles. Call them pions. They don't live very long. So, as they come in towards the surface of the Earth, the first response is they're not going to live very long. Even if they were to travel as fast as the speed of light, they would only go a couple of miles and they would never get down to the surface. So you and I down here on the surface, we've got nothing to worry about, right? Except they're moving. So what happens to their clock as they move? Especially as they get close to the speed of light. It runs slower. So you would have thought, hey, they're not going to make it, they don't live very long. But according to their clock, they don't think they live very long. But you do. And so guess what happens? They come all the way down to the surface of the Earth and we detect this radiation, and that explains a lot of what we didn't really understand. How in the world could these crazy things get down here? And it was because their time is different than our time. And they do get down here. In fact, more of them get to a mid-range than all the way down to the ground. So fortunately, very few of them get down to the ground. But people who spend a lot of time in planes, like pilots and I was going to say stewardess, but what's the modern word? Flight attendant, thank you. Flight attendant. They keep track of how many hours they are up there because they get heavy exposure to radiation over a career. Yeah.
According to that equation, though, light photons travel at the speed of light, but when something travels at the speed of light, time just is infinite.
Right. Okay. So if I was watching a photon go across here, maybe it would take 30 milliseconds, or not even that. What is it? One nanosecond a foot. So maybe we're looking at 40 nanoseconds. All right. So if I were to put this into this equation, my time watching that is 40 nanoseconds. How fast do they travel? So infinite times 0. Perfect. Right? Now, obviously, there's a little more that needs to be going on here. We've got some limits, but you can do the L'Hopital's rule or the hospital rule of your calculus and take the limit and see that this is well defined. And we will get the idea that, from my perspective, it took 40 nanoseconds. From the photon's perspective, it took 0 seconds. No time. And so from the photon's perspective, it does not evolve. It doesn't change. There's no time going on, which that alone sounds pretty bizarre.
Okay,
What? Well, I don't know if you call that forever or nothing, because what's 0 time? I mean, time doesn't evolve for them. If my time were to stand still, my heart would stop, my brain function would stop, my emotions would stop.
That's what the photon would see us like, right?
Yeah.
And if you could be on the photon, you would see us stop.
Right. Right.
Whoa. That's a vacation.
All right. So you see, this is bizarre, and this is just the first of 3 that hopefully we'll get to before today's over. Yeah.
Okay, it was back to the twin thing.
Ah, yeah.
Sorry. Because NASA's actually do that, not with kids though, but they said
Yeah.
that they would come back younger.
Yeah, the kid came back younger. Remember? So the kid went out.
Yeah, but,
So the kid on Earth
okay, they didn't, yeah.
is the 20. I guess I did 10. The kid on Earth, the twin on Earth is 20. The toddler is on the spaceship.
Oh, okay.
Right. Yeah. And that's actually where I was starting to go with this. You said something about twins. No, we haven't done this with humans, but we can do this with subatomic particles that have radioactive lifetimes. And these do check out to be absolutely fine. So despite how bizarre it does seem, it explains a lot of what we observe that could not be explained with Newtonian physics. And so that's how modern physics works. I mean, let me take you back 2,000 years ago. To me, this is just bizarre, as probably someday people will be talking about time. But when Aristotle stood up in front of the Greeks and said, you know what, this rock weighs 10 times more than this one. So if I drop it, doesn't it seem reasonable that this would fall 10 times faster? Well, Aristotle said it must be true. Everybody believed it for 2,000 years. Finally, Galileo gets up there and he gets on top of the Leaning Tower. I don't think it was leaning by then, but Tower of Pisa. And he goes, here's a rock 10 times heavier than this one. I'm going to drop it. Wait, now what did Aristotle say? 10 times faster, right? Nope. They hit the same. You don't believe me? I'll drop it again. So he goes down, picks it up, he drops it again. Now, you can either believe what really happened, or you can put him in jail, which they put him in jail. So, so that's where we are. We are at a place that this is what seems to be really happening. You can either accept it or put me in jail. Your choice, you know. And that's just how the experiments work. And so we don't have a good way of really figuring out exactly why yet. And I say yet, not we as scientists yet, but me explaining it to you yet. There is obviously more to it, but this is the teaser, if you will. This is the beginning part, because didn't everything kind of fall in line with time? Didn't we have things like momentum, velocity, angular momentum? Everything depended on time. We got to change it. Everything. This is not just a minor modification. This changes the foundation of our understanding of the world around us. Fortunately, only when we get close to the speed of light. So it is a big step in science. It's probably a little step in terms of engineering. All right. Well, with what little time I have left, let's keep going with this. An extension of this might be, let's get back into our train again. Here's the train. Let's say the train has a length L. Let's say I'm in the train here. I'll not worry about my flashlight anymore, that I'm in the train here. And I'll take two views of it again. Let's take your view from the outside. Let's take my view from the inside. Now, as you look at the train, you would probably say, here is the velocity of the train on the outside. Now, it's difficult for me to say what the velocity is of the train from the inside, so that's not really quite what I mean. But what I could do is I could look out of the train and see you move, right? And so at what speed do you move? It seems like it might be the same speed but opposite in direction, right? And that's what Einstein says. He said, well, wait a minute, it probably is. There's something interesting about speed. Not only did it lead to this discussion about the speed of light, but what was also kind of interesting here is that there seems to be something symmetric about it. So here's Einstein's approach. He says, what if those two are the same? Let's kind of have that same discussion that we had here. If those two are the same, then if I go to measure, say you go to measure the speed of the train, you probably would do this. You would take what is the length of the train as observed by you on the outside divided by the time as measured by you on the outside. Over here, I would probably say, what is the length of the train as measured by me from the inside, and what is the time measured by me on the inside? Uh-oh. See any troubles here? Are these times the same now? So what does that mean here? The lengths are different. So if we're going to open the window to let times being different and speeds still being the same, a consequence of that is lengths will not be the same. And so when I ask you how long is my train, you observe a different length than when I say what is the length of my train. And in fact, let's do this. How much length would I call this train? Well, let's start here and ask which one has the proper time. And before you answer that too quickly, let me pause and ask yourself, how do we measure proper time again? How do you get velocity? Distance divided by time? Yeah. So let's think about how you might measure the speed of the train. You would probably stand back and you might actually paint a mark on the ground right here. You might kind of hold a watch in your hand and say, when that front edge of the train gets here, I'm going to start it. And when the back edge gets to that mark, I'm going to stop it. Fair enough? And so your focus is this mark. Fair enough? Start, stop. Any movement between you and that mark? How about me and the train? How would I measure the length of my train? I might say, okay, when my front edge gets to that mark, I'll start my watch. When my back edge gets, I'll stop it. Which one got proper time? The outside. And so this is the opposite of what we just did. Remember last time the proper time was on the inside. And the reason for that is really the experiment, the thing we were observing was on the inside. Now the thing we're observing is on the outside. And so I'm going to put here a delta t sub p. And so now you're doing proper time as you would measure the speed of it. And I would measure non-proper time, so I will put a delta t. And let me just emphasize, because those two numbers are different, then the lengths are going to come out to be different. How much different is going to be easy to calculate now, because in place of this non-proper time, I'm going to put gamma multiplied by proper time. And so that was our discussion here, is that we can go from one to another. So I'm in the train and I will measure a non-proper time, but I could get out my calculator and figure out what proper time is from that calculation. And then of course we each have proper time, which cancels off. And so the length that I see from the outside observer is equal to the length as the inside observer divided by gamma. Now I'll remind you, gamma has what range of numbers? Starts on a low speed with a range of 1 and goes to infinity. So what would this say about the length you would see my train? It would be smaller, right? And so just like we talked about moving clocks run slow, here we will say moving objects shrink. They don't become the same size. In fact, how much would they shrink if you're going the speed of light? You guys brought up the photon. And it's probably not good examples because those are so extremely bizarre that they just make things worse. But you asked about the photon going from that side to that side. I said it took 40 nanoseconds. On the photon's point of view, it took 0 time. That may bother you. How in the world could it go that far in 0 time? Answer, how far did it travel? 0 speed. I mean 0 distance, right? Because what's gamma? Infinite. So how far is it from that wall to that wall? 0 distance. So the photon traveled 0 distance in 0 time. And 0 divided by 0 is speed of light. Yes? or at least in the limit. And so the photon does go the speed of light. Both from its perspective and our perspective, the photon goes the speed of light. It just travels a short distance over a short time, just like these trains. You guys looking on the outside are going to look at this and say, the train has a small length to it and doesn't take much time. I, being in the train, would say, no, it has a longer length and takes a longer time. But either way, we get the same speed. We just don't get the same length to the train, and we don't get the same time to the train. Well, maybe I should even put, we refer to this as length contraction. And so objects get smaller. The moving clocks, I guess I should have put, is formally referred to as a time dilation. And so we've got our moving clocks run slow, is a nice slogan, if you will. But I guess the more formal is it is time dilation. And that is length contraction. And so the things are not quite as long. And I know these are bizarre. In fact, for years I've asked Don, I said, you know, this is so hard to get across to students, it's just bizarre. And if they haven't been pre-exposed to it, it's just kind of hard to sink in. You got anything really good for me? He goes, well, I can give you a meter stick and you can try to throw it real fast. So we did, it didn't work. So Don said, I'll throw it real fast for you. All right. And here's what we get after Don throws. No, just kidding, it broke. But I like I said, it's hard to kind of digest what this really is going on. So, now that we've seen two of the three beginning bazaars, let's see if I can help you understand it a little better. And it will also lead into our third bazaar one and be a good wrap up of our time, yeah.
For the length contraction, it only contracts along the direction in which
Good point.
it's moving, correct?
Yes. And right, and I think my next diagram, you'll see that a lot better. But to answer your question, yes, this is a contraction in the movement or in the distance it moved. Yeah. And so, again, we're back to that same dilemma. Oh, and before I completely erase everything and go to my drawing I said I would, let's pause. And I just called it inside and outside to try and help, but you will see it as proper and non-proper lengths in your book. So let's use that same definition. Which one would be the proper length? And I thought I even wrote it down somewhere in my notes, but I guess not. And maybe before I completely answer that, what one was the proper time? It was this one, right? Outside? And again, why do we call this proper? Because there's no motion, right, between what we are using to measure time. So I erased it, but that little mark there, you guys on the outside would have done this. Front edge, back edge. There would be no motion. But what about length? Who would measure the proper length? The guy on the inside, right? Now, if you think about how I'm going to measure the length, let's say I'm in the train. Let's say that door and that door are the inside walls here. As I look at that wall and I look at that wall, I'm going to measure the distance between them. There would be no, and here's where it gets a little different, there'd be no motion between those walls. Now, not me. I might have to go over there and put my meter stick down, and I might have to lay it out here. But there's no motion between that wall and that wall. That is going to be our proper length. Whereas you on the outside might sit over here and say, okay, I'm going to go to the front of the train and measure it. And then I'm going to go over to the back of the train and measure it. But by the time you go to measure the back of the train, the position the back of the train was when you started your measurement is now different than when you finished your measurement. That's the non-proper. There's motion involved there. And so this is then the proper length, and this then is what we call the non-proper length. Did I get that right? Oh, there's the inside. Proper. Sorry, proper. It looked funny. Okay, good. And so that's why the length I get for the proper is always going to be the biggest one. Then divided by a number greater than 1 is always going to give me something smaller. And so I have my length contraction. My moving object is a little bit smaller. Okay, well, as I said, I thought before we do the third one, we should see if this gives us a little better understanding. I'm going to draw a picture here. And for a moment, let's not even worry about all this stuff we already said here at the beginning. Let me just do a simple kind of experiment that at first may look like it has nothing to do with what we've discussed so far. And so just take everything we said and just put it on the side burner here for a second. And let's have a new discussion here. Let's do this for a moment. Let me take the x and y axis, and let me take an object. And I grabbed this metal rod for this purpose, and say, if I were to put this metal rod, say, here on the x-axis, and then as time goes on, I'm going to let it move with a constant speed, and at first let me just make it go up. All right, so here's the rod, about this long. It would be here, heading up at some speed. A little bit later, it would then be here. Fair enough? And perhaps still moving at that same speed. Now, what if my grid was at a different angle? Or, put another way, what if my object was tilted but still going at that same speed? Okay, so I guess I would have something like this. And I would be traveling at that speed. And so a little bit later in time, try to get about the same distance. I'd be about there. That's what it would look like, right? And if I go to talk about the motion of it, I guess over here, I would say this edge right here has a vertical speed of v. It has a horizontal speed of nothing. Fair enough? But this one over here, that is now tilted at some angle theta, now has a vertical speed of what I would say would be v cosine of theta, and would have a horizontal speed I wonder if I want that theta. Well, I'm going to ignore the theta anyways. But the vertical would be cosine if I use this one, right? And the horizontal will be sine, which is a little different than the angle we did when we did the train and the flashlight one. I did the other angle. But my point is that the movement of this object through x and y, you might say, is the same speed. However, the movement is a little different along the x-axis and the y-axis. Okay. Because let's talk about making a plot of something moving through time. Remember, we started this discussion that, hey, the flow of time is different for different people. This is like a movement. And so if I were to take this rod and I were to put it right here on the x-axis, then of course from your perspective you say, hey, this is not moving. Now I would say it's not moving on the x-axis, but it is moving like you're moving. We're all moving through time. And so if I were to plot this thing in terms of time, I guess I would start here, just like this one. I would say it evolves at some rate. Let me call it the speed of light for just a second. After a little bit of time, it would now be here. And this thing has, quote unquote, moved through time. You too have moved through time. So if you were sitting over here watching it, you would of course now be here, and of course you would say, oh, it didn't move. No, it didn't move in space, but it moved in time. There was a flow in time. The reason I bring that up is because what if that rod kept its same speed no matter what I do? Just like this discussion. This rod kept its same speed. But the difference between here and here is that this one is now moving along on the x-axis. And so this one, instead of going up to here, goes over to there. It still moved through space and time at the same rate here, just like this analogy is, this moves through space the same. It just here's only the y-axis. Here's the x and y-axis. Here, this one, instead of moving just through time, it now moves through a combination of space and time. What does this part mean along the x-axis? Well, that would mean it's moving, right? And so this rod would actually move on the x-axis. But notice, because it is now moving on the x-axis, it's not moving as fast on the y-axis. That's what happened here, right? If we kept the total speed the same, now that it moves along the x-axis, it can't move as much on the y-axis. If it had only been moving in the y-axis, it would have gone to here. But because it is moving a combination, it's a little shy of that. This you might call the delta y. The fact that it is a different amount of distance in this view versus this view. Over here, then, that would be a time difference between the two observers. Because if I am the observer here and I do not move, I would go up to here. And so my time went this far. The moving object's time only went that far. We have a difference in time. There is a time dilation. And notice then, the amount of time dilation, doesn't it depend on how fast you're going? And what if you went all the way at the speed of light horizontally? How much do you go up in time? None. And so, as we're hopefully beginning to see, maybe this isn't quite as bizarre as it seems, or maybe even it's more bizarre, to say, there's nothing real special about this length contraction and time dilation other than the fact what we really have is everything in the universe is moving along at the speed of light. Now, if you say you're not moving, that just means you're moving along in time at the speed of light. And the more you move in space, the less you move in time. Just like over here, the more you move on the y-axis, the less you have on the x-axis. The more you move on the x-axis, the less you move on the y-axis. But your total speed never changes. And so our discussion and our discovery here is we do not have space and time anymore. These are connected together. We have space-time. And I know it's just a subtlety in words, but it is profoundly different. And you'll hear that as we go through this chapter. It's not space and time, it's space-time. You affect one, you affect the other. In the same way that if you had constant motion in an xy plane, if you affect the motion on the x, you also affect the y. They are interconnected together. One plays a role on the other. And so this, hopefully, gives us a little bit of an idea of why there is time dilation. Because time is really just another coordinate. Maybe you've heard that phrase. We don't live in a three-dimensional world. We live in a four-dimensional world. X, Y, Z, and T. You, me, everyone around us, we are all moving outward at the speed of light. Most of us are moving along the time axis at the speed of light. Once in a while we get in a car and we adjust our motion of time from being along, our speed from being along the time axis to being slightly off of the time axis, and so we have a little bit of motion on the x-axis, but we still have most of the motion along the time axis. And if you were to go really, really, really fast like the twin, you may have so much motion on the x-axis that you have little to no motion on the time axis, and so time flows, time evolves at a much lower rate. Let's look at the other one. Maybe changing colors could even be help here. Because our first bizarre consequence was right here. It was time dilation. But do you also see length contraction? If this is the length of the rod, so here's the rod. And right now, this rod is moving only along the time axis. And so you'd say here and here is its length. But if this thing would be to rotate off the time axis, which again, it can't really show it in this room, but I can do it on the xy axis. If I tilt it on the xy axis so it moves this way, how long would I say is it on the x-axis? Wouldn't that be the idea? And wouldn't that be a little bit smaller? And that is our new length. That is what this picture is trying to show here. That as we look up on this length right here, this is our length, which is our proper length divided by gamma. That gamma factor is an indication on how much you have rotated your motion in space-time. Again, notice I didn't say space and time. It's how much I've rotated my motion on a space-time axis. Does that help at all? Because if that picture's making any sense to you, let's try the last one here for today. Coming over to here, I would say, as this goes straight up, the two endpoints of my rod are always at the same Y location. Fair enough? Once I tilt it and have some motion to it, then my two endpoints of my rods are at different locations on the y-axis. As we take this over here, then that edge of the rod and that edge of the rod would be what? At different moments in time. Let me explain it this way. Let's say I had two firecrackers at the end of this rod. Then, at some moment in time, up here, observed by this, let's say this is you right here. So here's the rod, firecracker there, firecracker there. You're not moving compared to it. And so this rod moves along on the time axis. You move with it. Your moment in time is the same moment as each of the ends. The firecrackers go off at exactly the same moment in time. You watch it and you say, all right, which firecracker went off first? You say? Same time. But somebody else going by in a spaceship sees what? They see the rod looking like this. It's shorter. The time it took to get there is less. And more than that, the two endpoints are at different moments in time. So if somebody goes by in a spaceship and they look at the firecrackers, what do they see? Two explosions at different moments in time. And so we have what I call the third bizarre consequence. We lost our simultaneity of the situation. Things that one person says happened at the same time, another person says, nope, that one happened first. And so we ask, who won the race? One group of people, oh, it's a tie. Another person, they won versus them. No. Third person said, no, that one beat that one. Who's right? You're all right based on your perspective. So, let's see if this video helps. Because I think this is a video put together really, really well. It doesn't do the twisting of the axis, but it does show how if you are going to have the speed of light be the same for each observer, then you can't have the two events happen at the same time. Watch this one. Of course, not a surprise, it's a train. And they got lightning bolts instead. What? That'll go out of the way. Oh, good. All right, but let me start it over. But watch this one. Where's the sound?
Imagine two observers, one seated in the center of a speeding train car, and another standing on the platform as the train races by. As the center of the car passes the observer on the platform, he sees two bolts of lightning strike the car, one on the front and one on the rear. The flashes of light from each strike reach him at the same time. So he concludes that the bolts were simultaneous, since he knows that the light from both strikes traveled the same distance to his eyes at the same speed, the speed of light. He also predicts that his friend on the train will notice the front strike before the rear strike, because from his perspective on the platform, the train is moving to meet the flash at the front and moving away from the flash at the rear. But what does the passenger see? As her friend on the platform predicted, the passenger does notice the flash from the front before the flash from the rear. But her conclusion is very different. As Einstein showed, the speed of the flashes as measured in the reference frame of the train must also be the speed of light. So, because each light pulse travels the same distance from each end of the train to the passenger, she can only conclude one thing. If she sees the front strike first, it actually happened first. Whose interpretation is correct? The observer on the platform, who claims that the strikes happened simultaneously, or the observer on the train, who claims that the front strike happened before the rear strike? Einstein tells us that both are correct within their own frame of reference. This is a fundamental result of special relativity. From different reference frames, there can never be agreement on the simultaneity of events.
All right, so that is bizarre consequence number 3. There's more, and so your answer on the test is all relative, huh? And we're so tight on time, but I'd hate to get halfway through one of these discussions and stop. So I guess we'll stop early. You guys can go tell your friends that it's an easy class. We always get out early. They'll sign up next year and that. But I hesitate to start the next one without more time.